Hello, everyone. So my presentation talks about a sweeping process framework for an optimal multifunctional material. So for this presentation, to keep it short, we consider one system. One second. Here you go. So we have this system of springs given in the figure here, and for our system, we consider that each spring conducts electricity and each spring is elastoplastic. So since each spring is elastoplastic, there is some achievable stresses for each spring I. And we define those elastoplastic stresses in terms of this. So we have that for every spring I, the elasticity bounds are taken to be negative Ci and positive Ci. And again, there is something for certain kinds of materials, we can have a relationship between the elasticity bounds and the resistance of the springs. So for each spring, we have a certain resistance in terms of the elasticity bounds, and the resistance for each spring I is given as 1 over Ci as defined here. So as you see, there's a displacement control loading between node 1 and 4 here. So upon gradual stretching, certain springs goes into plastic mode and the response force increases until a certain terminal value. So we kind of work with two functions. We're trying to find an optimal material in terms of the terminal response force and the resistance of the material. So we work with two factors. We have the terminal response force that we calculate for this system, and we calculate the resistance of the system to find an optimal multifunctional material. Okay, so for terminal response force of the system, we have some previous publication that gives us good results, that gives us formulas for the response force for the figure 1 here. So the response force can be classified in terms of these three formulas. Now, if our elasticity bounds satisfies these inequalities, so suppose if our elasticity bound satisfies inequality number 1, then we can say that the system, the displacement control loading forces the springs 1, 3, and 5 into plastic mode, and the response force of the system is given by C1 plus C3 plus C5. So that's one of the cases, and we can have three formulas. One where the response force is C1 plus C3 plus C5, the second where the response force is C2 plus C3 plus C5, and the third one is where the response force is C1 plus C2 or C4 plus C5. Now, for simplicity here, we consider the last case where the response force is C1 plus C2 or C4 plus C5 to be the same. So just to compact everything and have results, like we use Mathematica to find the optimization results. So for the last case, for now, we considered C1 plus C2 equal to C4 plus C5. So these formula cumulatively gives us the response force formulas. And the other thing that we are trying to optimize is the resistance of the system. So the same system given in figure 1 can be redrawn as figure 2, and it is nothing but a Wheatstone bridge. And where every spring I has resistance 1 over Ci, we can find the formula, we can use Kirchhoff's law to find the formula for resistance and conductance of our system. So now we have two things. We have a formula for the terminal response force in terms of Ci, and we have the formula for the total resistance of the system in terms of Ci. So now we propose our optimization problem. So we're trying to optimize the problem in two functions. We want to maximize the response force, and we also want to maximize the resistance of the system or the conductance. So we look at both the cases where we maximize either resistance or conductance. And since it's a multi-objective optimization, we introduce K1 and K2. So we scalarize the objective function and then try to find a Pareto optimal solution set. So let's talk about the constraints. So corresponding to different response force, we have some feasibility conditions on the springs. This directly comes from a paper that was published before. So we have some feasibility conditions for corresponding to each response force formula. And for the third case where the response force is either C1 plus C2 or C4 plus C5, the constraints are exactly the opposite of what we have here. So for example, we had negative C2 less than equal to C3 plus C5 less than equal to C2. So for this one, we have negative C2 is greater than equal to C3 plus C5, or C3 plus C5 is greater than equal to C2. So basically, whatever is not being satisfied here is all the conditions that we take for the case 3 for the response force. Now, there's also a positive correlation of cost of the material with the elasticity bound. There are a few papers that give you the cost is directly related to the elasticity bounds. So we do consider a fixed cost of the material. So we add another constraint that says that the cost of the total material is subjected to be 1, so that we fix it in terms of finding an optimal material. Sorry. 1 second. Okay. So the maximum value for the response force in itself, if we consider a single objective optimization, if we just have the response force instead of having resistance and conductance, and we have all the constraints mentioned above, the maximum value of the response force comes out to be 0.5. So to have some minimum strength of the material, we have another bound on the response force. So we always take the response force to be greater than equal to 0.45. So these are all the constraints that we take for optimizing our system. And then we get some conclusions. So I basically used Mathematica to solve this optimization problem. The graph here represents K1 and K2. So K1 changes from 0 to 1 and K2 changes from 0 to 1 with 0.1 step size. And these circles represent, so basically the radius of each circle is the optimal value at that point. It's the optimal value for our objective function at that point. So just to see what we're getting, if we do this, we notice a few things here. We notice that almost in every case, the maximum is attained on the boundary of the 3 domains. Again, we get almost identical results for all 3 different scenarios. So 3 different scenarios here talks about the different formulas for the response force function. Okay, so we also see that whenever K2 increases, the function grows linearly, whereas whenever K1 increases, there is a slight increase. It's almost constant. There's only a slight increase in the function. We also notice that in almost all the cases, the optimal value satisfies these formulas. The optimal values of Ci satisfy these equations. So C1 equals C5, C2 equals C4, and C3 equals 0.1. So this is the result where your objective function is the response force and resistance. So we're trying to optimize the system in terms of response force and the resistance. So we did the same thing with conductance, and we get the following results. So for when we have the response force and the conductance, we get slightly different values for the optimal values of Ci. We also see that the response force always takes the value of 0.5 in this case. So our response force is always greater than the defined value, and we always have the ideal value for the response force. Again, we have certain different values for each Ci based on, okay, so this is based on the different values of response force. We have C1 equal to C5 in 2 cases, and C2 equal to C4 and C3 equal to 0. And for another case, we have C1 equal to C4 equal to 0, or C2 equal to C5 equal to 0. So either these 2 springs are 0 or these 2 springs are 0, but in every case, we always get that C3 is equal to 0. That means that the spring does not, that we don't have that spring. So that's about it. Thank you.
Thank you.